So this video is going to cover examples where we use Rolle's theorem from section 3.2. And I'll work through these three examples and then do another video covering how to applying the mean value theorem. All right, so continuing where we left off, Rolle's theorem. There's certain conditions we need. We need f of x, the function, needs to be continuous. On the closed interval AB. It needs to be differentiable on the open interval AB. And that just means its derivative has to exist on the entire open interval. All right, then we need to check that the endpoints equal each other. You need f of A equal to f of B. All right, if that's the case, then there exists at least one C in the open interval AB such that its derivative is equal to 0. All right, that's Rolle's theorem. So we'd have three things we need to check, and if these things if they work out, then we apply where we find this value C, where its derivative is equal to 0. Okay, so number 13. Oh, it's on the interval 1, 3. All right, so we need to check the conditions. Now, this is a polynomial that's in factored form. So f of x is a polynomial in its factored form. So what does that mean? So for a polynomial, we know it's going to be continuous everywhere. And differentiable everywhere. So the two conditions hold out. So we have the first condition is that f of x is continuous on the closed interval 1, 3, since it's continuous everywhere. And I'll use CONT for continuous, and then on 1, 3. So that checks out, and then its derivative exists on the open interval 1, 3, or it's differentiable. So I'll use DIFF for differentiable. All right, so then we need to check that f of 1 equals f of 3. Right, that's the, so we met this one and that one. We need to check this. And it does, because if you plug in 1, so where it has x minus 1, it becomes 1 minus 1, and then 1 minus 2, then 1 minus 3. The thing is 1 minus 1 is 0, so this whole thing's going to equal 0. And f of 3 is going to be 0 also because of the x minus 3 becomes 3 minus 3, which is 0. But plugging it in, it'll look like this. So the 3 minus 3 is 0, makes the whole thing 0. All right, so we've met the third requirement. So we're good to use Rolle's theorem. So we need to find C, or all values C. Find all C where its derivative is 0, where f prime of C equals 0. Now the function, I'll rewrite it. So it's x minus 1 times x minus 2 times x minus 3. Now suppose you could use product rule through, but because we have x minus 1 times x minus 2, that's a product, and then x minus 2 times x minus 3, that's also a product. Instead of doing that, I'm going to expand the polynomial. And if I were to expand it, so I'll first expand out the x minus 2 times x minus 3. All right, that's going to make this x squared, and then minus 3x and minus 2x makes minus 5x. And then minus 2 times minus 3 plus 6. All right, so that's what that is. Now I have to multiply x minus 1 by that whole thing in green. So I distribute x. That attaches an x to each term, so x squared becomes x cubed. Minus 5x becomes minus 5x squared, and then x times 6 is 6x. And then now I multiply negative 1 through every term. That's going to make this negative 1 times x squared is negative x squared. I'm going to go ahead and write it vertically like this, so I would going to combine it with the negative 5x squared since those are like terms. Negative 1 times negative 5x is positive 5x, so I'll put that below the 6x since those are like terms. And then I have negative 1 times 6 is minus 6, and then I'll just add vertically. So that's going to turn into minus 6x squared plus 11x minus 6. All right, so that's f of x. Now I'm going to find its derivative. And you could have done product rule, and it probably, it still required a lot of, not like a lot of work, but a decent amount of work to expand the polynomial. But I'm going to I expanded it out to just use regular derivative rules. And so f prime of x, the x cubed becomes, you drop the 3 down, so it'd be 3x to 3 minus 1. And then minus 6 times x squared, derivative of x squared is 2x. So it'd be 6 times 2x to the 2 minus 1, plus 11x. Well, 11 times 1 because derivative of x is 1. And then 6 is a constant, so its derivative is 0. So the derivative f prime of x is equal to 3x squared minus 12x plus 11. Now I need to find all values c where this is going to equal 0. So I set f prime of x equal to 0 and solve for x. So I set 3x squared minus 12x plus 11 equal to 0. And to solve for x, this is a quadratic equation, so I'm going to use the quadratic formula. So this is a quadratic equation. So use quadratic formula. And the quadratic formula, go ahead and write it down. All right, so plugging in everything into the quadratic formula. So A is 3, B is -12, and C is 11. So when I plug it in, since I have negative B and B itself is -12, I have negative times a negative makes positive. So that's really positive 12 plus or minus the square root of B squared. Well, that's -12 squared. And make sure you have the parentheses. All right, because without the parentheses, this becomes negative, whereas with the parentheses, it's positive 144. And then -4 times AC, so that'd be -4 times A is 3 times, and then times 11. All of that's divided by 2 times A, so that's 2 times 3. All right, so if I multiply this through, -12 squared, it's 144. And then I'm going to be subtracting out 4 times 3 times 11, and that's actually 132. All that's divided by 6. So I have 12 plus or minus the square root of 12 divided by 6. And you can simplify square root of 12. So recall from algebra class, like if you had square root of 12, that's the same thing as 4 times 3. Well, square root of 4 is 2, so this is 2 square root of 3. So really, this is 2 square root of 3. And then I would just divide out. The common factor for all 3 components is that they all are divisible by 2. So I could divide 12 by 6. That's going to make that 2. And then 2 over 6. And 6 divided by 2 is 3. Sorry, so that's, I do 12. Actually, let me write it out like the following. All right, so this is what we have, and you have 2 possibilities. I could have 12 plus 2 square root of 3 over 6, or 12 minus 2 square root of 3 over 6. So up top, I can factor out 2, and that's going to make this 6 plus square root of 3. And then 6 is 2 times 3, so then I can divide out the 2's. And same thing for the other one, it's just going to be 6 minus square root of 3 over 3. This will be 6 minus square root of 3 over 3. So we have 2 values for x. Now they both better be in our interval, and our interval is 1 to 3, I believe, from the beginning of the question. Yeah, so 1, 3. Remember, we need it to be in the open interval. And you could think of this as x equals 2 plus the square root of 3 over 3. And then, because I would separate it as 6 plus 6 over 3 plus square root of 3 over 3. 6 divided by 3 is 2. And then this is 2 minus square root of 3 over 3. Both of these lie inside the interval. All right, so we found the two values for c. So there's two values for c where its derivative is equal to 0. All right, and it's 2 plus square root of 3 over 3 and 2 minus square root of 3 over 3. All right, and I just labeled it as C1 and C2. All right, and you could have put it as 6 plus square root of 3 over 3. I just wrote it so that it has, so it looks like it's more obvious that it's inside that interval 1, 3. All right, so recap real quick. So I first checked the conditions for Rolle's theorem. It was continuous and differentiable because it's a polynomial. It's just a polynomial in factored form. Then I needed to check the condition that f of 1 equals f of 3, and they do because they both are 0. All right, now I applied Rolle's theorem to find all values c where its derivative is equal to 0. And so I first expanded out the polynomial from factored form into its standard form, so that I got x cubed minus 6x squared plus 11x minus 6. Then I found the derivative. And then after I got the derivative, it was 3x squared minus 12x plus 11. I set it equal to 0. And used quadratic formula because that was a quadratic equation. Now this thing isn't factorable based on the factoring techniques we've learned up until this point from algebra class. So you'd have to use quadratic formula. And after I applied quadratic formula, all of this was just simplifying it. And I got down to here. And I needed to check, do both of those values lie in the interval 1, 3? And they do. So there's two values for c for which its derivative equals 0 for this question. All right, so this is number 15, f of x equals x to the 2/3 minus 1 on the interval, closed interval, -8 to 8. We're still trying to see if we can apply Rolle's theorem. Now this is an example where the function, it's continuous for all x in -8 to 8. But it's not differentiable in the open interval -8 to 8. And basically that means its derivative does not exist for all values in that interval -8 to 8. So f prime of x is not defined for every value x in the open interval -8 to 8. Now, how did I arrive at that conclusion? Well, I found its derivative. So f prime of x, using power rule, the 2/3 gets dropped down to its 2/3 to the x to the 2/3 minus 1. And then the -1 goes away because that's 0. So really this is 2/3 x to the -1/3, which you can bring that to the denominator. So it would be 2/3x to the 1/3. And raising something to the 1/3 is the cube root. So f prime of x is 2/3 times the cube root of x. So we can't have x be 0, right? Because then you would have 0 in the denominator. And so that's a problem because 0 lies inside of our interval -8 to 8. So therefore, I found a value where the derivative does not exist inside of that interval. So the derivative has to exist for every single value in the interval. So since that's the case, we cannot apply Rolle's theorem. So we just say Rolle's theorem doesn't apply for this example. All right, so I wanted to just do that one. So you have an example where the theorem does not apply. And that was because its derivative doesn't exist for every single value x in the open interval -8 to 8, since it doesn't exist for the value 0. As long as it doesn't exist for one value in the interval, then we can't say it's differentiable on the entire interval. All right, so the next one's number 21. So it's cosine pi x on 0 to 2. So we know the cosine graph is continuous everywhere. And its derivative exists everywhere because its derivative is sine, and the sine graph exists for all values. So it and differentiable everywhere. So f of x equals cosine pi of x meets the first two conditions, so it's continuous on 0 to 2, and then differentiable on the open interval 0 to 2. Now I need to check that the endpoints are equal. So check that f of 0 equals f of 2. All right, f of 0 would be cosine of pi times 0, which is cosine of 0. Well, cosine of 0 is 1. And if you plug in 2, that's cosine of 2 pi. So that puts you at the same spot as 0 radians. So that's also going to give you 1. All right, so f of 0 equals f of 2. Now I can apply Rolle's theorem. So find c so that f prime of c equals 0. And c is in the interval, open interval 1, 0 to 2. We don't consider the endpoints. All right, so f of x is cosine pi x. And by chain rule, sorry, it would turn into sine times the derivative of the inside function. So cosine of u, the derivative of cosine's negative sine, so it'd be negative sine of u, times the derivative u prime, where u is the inside function. In this case, u is pi times x. So u prime, the root of x is 1, so it's pi times 1, which is pi. So u prime is pi. So f prime of x is going to be equal to negative sine of pi x, since that's the outside function derivative, times u prime, well, that's pi. All right, so the derivative is negative pi sine of pi x. So now I set this equal to 0. So negative pi times sine of pi x equal to 0. Well, I can divide both sides by negative pi. And if you divide both sides by negative pi, you'll just have sine pi x equal to 0. All right, so I need to find x so that the sine of pi x is 0. And what I like to do is I'll think about it, well, if I just have sine of theta, when is sine of theta equal to 0? Well, that happens when the angle of theta is 0, pi, 2 pi, so forth. So really, this happens when we have n times pi, so it's a multiple of pi. So you could also have negative pi, negative 2 pi, and so forth. So it'd be n times pi, where n is an integer. So I can think of theta as pi times x. So sine of pi x equals 0 when pi x equals n times pi. So I just put pi x in the spot for theta. And then I solve for x by dividing both sides by pi. So you get x equal to n, where n is an integer. All right, so in integers, like you could have dot, 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 negative 2, negative 1, 0, 1, 2, dot, dot, dot. Now we have to consider what's our interval in question. And our interval in the question is 0 to 2, open interval. So we would not include 0. So obviously we wouldn't have any of these negative values, but we also would not include 0 since that's an endpoint, and we would not include 2 since that's an endpoint. So the only value we're going to have is 1. All right, so we found it. So our value for c is c equals 1. The value for c, where f prime of c equals 0, is c equal to 1. All right, and that's it for this example. And again, anytime I have some trig function like sine and you're taking sine of something equals 0, I treat it as if we had just regular sine theta equal to 0, and that, look where that is in a unit circle, and that's like at 0, pi, and 2 pi. If we go on infinitely many times, you'd have like 3 pi, 4 pi, and so forth. You can also have like negative pi, negative 2 pi, and so forth. So it's n times pi for theta. So then I just used theta in the spot of pi x and just replaced it and solved for x by dividing both sides by pi. So they both had pi, and so you just left with x equals n. And in integers, that's like negative whole numbers and positive whole numbers. Well, we need to take into consideration our interval is 0 to 2, so the only one that works is 1, because we could not include 0 and we don't include 2 since it's an open interval. All right, and that's it for this video. Next video, I'll cover some mean value theorem examples.